And welcome back. As we continue our cosmic journey, let's go ahead and transition to talking about eclipses of the sun and the moon, because these, of course, are things that we're going to observe within our sky. The first thing we have to understand when we're looking at eclipses is that Earth is pretty unique in the fact that we have a coincidence of size. One of the coincidences of living on Earth at the present time is that the two most prominent astronomical objects, the sun and the moon, have nearly the same apparent size in the sky. In fact, if we were to be at a different point in time, either much farther back in Earth's history or very far in the future, this would not align as well. Now, although the sun is about 400 times larger diameter than the moon, it's also about 400 times farther away. So both the sun and the moon have the same angular size. As a result, the moon, as seen from Earth, can appear to cover the sun, producing one of the most impressive events in nature. And that event is, of course, an eclipse. Now, any solid object in the solar system casts a shadow by blocking the light of the sun from a region behind it. This shadow in space becomes apparent whenever another object moves into it. In general, an eclipse occurs whenever any part of either Earth or the moon enters the shadow of the other. When the moon's shadow strikes Earth, people within that shadow see the sun at least partially covered by the moon, that is, they witness a solar eclipse. When the moon passes in shadow of the Earth, people on the night side of Earth will see the moon darken in what we refer to as a lunar eclipse. So let's first talk about solar eclipses, because these are some of the more famous ones. The shadows of the Earth and the moon consist of two parts. We have a cone where the shadow is the darkness, which we refer to as the umbra, and a lighter, more diffuse region of darkness called the penumbra. In our image A here, we can see a shadow cast by a spherical body. You'll notice that the dark umbra and we have the lighter penumbra. There are 4 points in the shadow labeled with numbers. Points 1 and 4 are both umbra regions, whereas 2 and 3 are both penumbra. Now, with our solar eclipse, if we were in image B here, you would see what the sun and moon look like in the sky at the 4 different labeled points. In position 1, it means that we would have a total eclipse. In other words, the moon is perfectly positioned in front of the sun. In positions 2 and 3, we'd have what we refer to as a partial eclipse, because it does pass in front of the sun, but you notice it's not a complete alignment. In position 4, the moon is farther away and thus cannot cover the sun completely. This can sometimes happen because of just the various orbits that we might have. Now, a ring of light does show around the sun. You can see here, and the moon's trying to line up here, and this is what we call an annular eclipse. Now, why don't we have more solar eclipses? Why don't these happen all the time? Because, the sun and moon are always going up in the sky. Why don't we have this happen like once a month, for example? Well, if the path of the moon in the sky were identical to the path of the sun, which would be the ecliptic, we might expect to see an eclipse of the sun and the moon each month, which would be pretty cool. However, the moon's orbit is tilted relative to the plane of the Earth's orbit about the sun by about 5 degrees. As a result, during most months, the moon is sufficiently above or below the ecliptic plane to avoid an eclipse. Now, when the two paths cross, which is about twice a year, it is then that the eclipses are possible. So let's look a little bit at the geometry of a total solar eclipse. If the sun and moon are properly aligned, then the moon's darkest shadow intersects the ground at a small point on the Earth's surface. And you can kind of see that here in this image, how the eclipse path is right here. It's this tiny little reference point. Anyone on Earth within the small area covered by the tip of the moon's shadow will, for a few minutes, be unable to see the sun and will witness a total eclipse. At the same time, observers on a larger area of Earth's surface, who are the penumbra, will see a partial solar eclipse. And so, as I mentioned, it's kind of a narrow band that forms around this eclipse here. So, between Earth's rotation and the motion of the moon in its orbit, the tip of the moon's shadow sweeps eastward about 1,500 kilometers per hour along a thin band across the surface of Earth. This thin zone across Earth in which a total solar eclipse is visible is what we refer to as the eclipse path. Now, again, 1,500 kilometers is a pretty decent size, but if we expand that out to a region of 3,000 kilometers on either side of that eclipse path, we get a partial solar eclipse. So that's if you were in that area, 3,000 meters on either side of that path, you could still see some kind of solar eclipse. You may not get the total darkness, but you'll at least see something. Now, it does not take long for the moon's shadow to sweep past a given point on Earth. In fact, the duration of totality can, depending on where you're at, may be only a brief instant. But it might be longer. But the most you'll ever see of totality will never be more than about 7 minutes. So what does a total eclipse actually look like? Well, a solar eclipse starts when the moon just begins to silhouette itself against the edge of the sun's disk. Then we have a partial phase that follows, during which more and more of the sun is covered by the moon. After about an hour after the eclipse begins, the sun becomes completely hidden behind the moon. In the few minutes immediately before this period of totality begins, the sky noticeably darkens. Now, during totality, the sky is dark enough that the planets become visible in the sky, and usually the brighter stars do as well. After totality, the sun slowly reappears and repeats the partial phases, just kind of in reverse, until the moon passes the sun. And that gets us into this last little bit about the total eclipse, because if we do have a total eclipse, what does this actually look like in our sky during totality? Well, during totality, as the disk of the sun becomes hidden behind the moon, the sun's corona actually becomes visible. Now, the corona is the sun's outer atmosphere, consisting of gases that extend for millions of miles in all directions from the sun. Now, the corona is always there, but it's ordinarily not visible because the light from the underlying layers of the sun are simply just too bright, so we can't see them. However, when the sun's visible disk is blotted out by the moon during a total eclipse, can we notice the pearly white corona? Now, of course, that was the eclipses of the sun, but what about the eclipses of the moon, those lunar eclipses that we had talked about? Now, a lunar eclipse occurs when the moon enters the shadow of the Earth. So we were kind of, instead of the moon blotting the sun, now it's the Earth blotting onto the moon. Because just as the moon can do shadows, the Earth also has a shadow. Its dark shadow is about 1.4 million kilometers long, so at the moon's distance, this covers about 4 full moons. Now, unlike a solar eclipse, which is visible only in certain local areas on Earth, a lunar eclipse is visible to everyone who can see the moon at that given time. Now, because a lunar eclipse can be seen from the entire night side of Earth, lunar eclipses are observed far more frequently from a given place on Earth than are solar eclipses. So with a lunar eclipse, what does this actually end up looking like? So, first thing we have to understand is that an eclipse of the moon is total only if the moon's path carries it through Earth's umbra. Remember, there are 2 regions, which is the penumbra and the umbra is that dark region. If the moon does not completely enter the umbra, we'll have a partial eclipse of the moon. But because the Earth is larger than the moon, its umbra is also larger, so the lunar eclipses can also last longer than solar eclipses. Remember how we said solar eclipses are a maximum 7 minutes. Lunar eclipses can easily exceed that. So what does the lunar eclipse look like? Well, we know with the solar ones, we can see the corona of the sun, but with the lunar eclipse, these only take place when the sun, earth, and moon are in a line. And the only time this happens is when the moon is opposite the sun, which means that our moon has to be in its full phase before that lunar eclipse can happen, which actually makes the darkening even more dramatic. Now, about 20 minutes before the moon reaches the dark shadow of the Earth, it's going to dim somewhat as the Earth partly blocks the sunlight, because remember, there is the penumbra region. And as the moon slowly begins to dip into the shadow, the curved shape of Earth's shadow upon it will soon become apparent. Now, when total eclipse, the moon is actually still faintly visible. It doesn't disappear kind of like the sun does. And instead, what it usually happens is it appears to be almost a dull coppery red. And the illumination on the eclipsed moon is actually sunlight that has been bent into Earth's shadow by passing through Earth's atmosphere, which is, because remember, the moon does not self-illuminate, so what you're actually seeing is still sunlight that has simply just been kind of manipulated by Earth's atmosphere, so that's why we get this kind of red tone. Now, I did mention that a lunar eclipse can be longer than a solar eclipse, but how long? Well, the whole duration of the eclipse depends on how closely the moon's path approaches the axis of the shadow. So for an eclipse where the moon goes through the center of Earth's shadow, so right through the heart of the umbra, Each partial phase consumes at least an hour, and totality can last as long as 1 hour and 40 minutes. Since the full moon is visible the entire night side of Earth, the lunar eclipse is visible for all those who live in that hemisphere. Now, total eclipses of the moon occur on average about once every 2 or 3 years.